So, did you get the link to the Dropbox folder? Yeah. That's good. And I'm going to work out of IPython just in a terminal because it'll be easier than pulling up the whole Canopy window, but IPython's at the bottom of Canopy window if you want to start it. Alright, so first talk a little bit about NumPy and just the basics of it, and sort of so you can get an understanding of what NumPy is and what a NumPy array is and how to hold data. So I'll just show you what it looks like. When I open IPython without the pylab command, which already imports NumPy, I'm just going to open regular IPython and import NumPy myself. Call it NP. You import something as something else. Or you can call it whatever you want, but NP is just the convention. And so here's a little data array where you name it and equate it to this function numpy.array, and inside of that is basically a Python list. This is the standard way to make a list in Python. It's just numbers separated by commas, and those become data points in your array. And so it's different than a Python list because NumPy it does a lot of the processing in C instead of Python, which makes NumPy faster. So once you have it, you can just look at it like this, and it shows you what it is. And each point has a data type, and so these are just integers. But you can look at your array and find out what data type it is by just seeing the d type, .d type at the end of it. There's a lot of dot things at the end of it that you can learn things about. So you can change the data type of your array. These are integers right now, so you can do math on them. But if you wanted them to be strings, basically words so that you can use them, you can change the type of it. So make a new one. String array is equal to my array. And then another NumPy function is as type, and string is an object that it's now a string array. So its data type is now a string. If you what? If you hadn't imported NumPy, it would. This NP come up would say no module, no function named NP. All right. So I'll show you the difference between integer array and a string array. So for each item in this, I'm just going to print that item times 4. So with the integer array, it multiplied those. Then for this string array, you can't do math with strings, and so it just adds them 4 times together in a line like that. And yeah, so that was basically just a Python list. This one-dimensional array, as it's called, is just a list of numbers. But where NumPy is really used for is in multi-dimensional arrays. So where you have rows and columns, basically like an Excel table or that sort of thing. Or a 2-dimensional array would be like an Excel table, and then a 3-dimensional array would be like an Excel table with stuff on the inside of it, with a little array on the inside of each. Yeah. And so for that, you have the outside brackets, and then you have points inside of it. So for like an image, you would have rows and columns of the image, and each pixel would be an RGB value. So there'd actually be 3 numbers inside of each value. So this is a 2-dimension array, and we can see how many dimensions it is, what .ndim. And then this one is pretty useful. .shape, which tells you it's a 3x4 array. This dim2 array, it looks like that. It's 3 columns and 4 rows wide. Yep.
I work a lot with most two-dimensional arrays. It's often
Yeah.
spreadsheet stuff.
Yeah, me too. Besides images, 3-dimensional, I don't go to 4-dimensional because I can't really think of that many uses for it other than, you know, yeah, or just some sort of more complex data set with, you know, different things in it. If you say the size, it just tells you how many things are in it. And so NumPy is great because it's fast doing math. And we can just get the mean of this array by using the function numpy.mean. And that got the average of all of the numbers in there. But it's important to be able to do math on a column by column basis or a row by row basis if you want to see the average of all your rows, just like you're dragging in Excel. So they use these kind of hard to remember things, axis. So if we gave it numpy.mean and tell it which axis to calculate it on, 0 is going to be this axis here, so it's the average of each column.
Okay, so it's going to be here, the mean of each 0 element in each list that makes up the two-dimensional array?
Yeah, so axis equals 0 just means it's going to do the math column-wise.
Oh, okay.
As opposed to row-wise.
Axis 1 means it's going to do a row-wise.
Yeah.
Okay.
So then it gives me a new array. When you did the math, it gave you all these values in a new array. And so this is row-wise because there's 3 rows there. And then where you do most of your work in NumPy is indexing arrays. And so dim2 array indexing at 0. So the first item in this was this 0, 1, 2, 3. And then the second item is 0, 1, 2, 3. Third item is 0, 1, 2, 4. But Python starts at 0. So if we have this array indexed at 0, those brackets, you're just going to get the first item in it. And slicing with indexing, this just means all rows, all columns. So this doesn't change anything about our array. But if you have, basically, now you're going to get this from 0 to 2 rows if you index it like that. That's just the first 2 rows there. Start it from nothing to 2. It would be the same thing as if you wrote 0 to 2.
So it's just like slicing in the list.
Mm-hmm. Yep. So NumPy starts with rows and then columns, and it's just one of those things you have to remember. So if I do 0 to 2 and then all rows, that's the same thing as just 0 to 2. If I do 0 to 2 and then 0 to 2 columns as well, the comma in between, it's going to give me just that top right corner of it. So, yep, you can just get the columns that way. So yeah, this is just one thing you sort of have to memorize, how slicing works. It's not super intuitive. So if I take the first item in this dim2 array, and this is just a special type of slicing that reverses it. Colon, colon, -1. It's just a stupid thing to memorize. And that will reverse your array. It was 0, 1, 2, 3, but if you put that at the end of it, it's reversed.
So the first index there is the same thing you want the first
yeah,
row.
First item. Yeah, the first row.
First row, and then the colon, colon, -1, so you reverse that.
Mm-hmm. Yeah, so you can index something you already indexed, and you can index it as long as you want. All right, so none of your data is ever going to look that pretty. 0, 1, 2, 3. It's going to look something like this. And I'm using IPython right now. It's great for learning and teaching people in. Usually you're writing scripts, and then this is just somewhere in your data. But you might want to look at it, throw it in IPython real quick and look at it, and it's going to look like this, since you did math on it, so there's tons of floating point numbers there. So one thing that is helpful is to actually put it into Excel where you can see what rows and what goes in what rows and what columns. That's where Excel is useful. It's easier to visualize. So let's see. In IPython, you can use it as a Unix terminal, basically. So that's what I'm doing. I'm just changing directories into my desktop. And I'm going to use this function, numpy.saveText. You might be thinking like, oh, I want to save this so that I can open it in Excel, but what is that function called again? And so if you, in IPython, if you start typing it and then you hit tab, it tells you everything that's possible. And so, oh yeah, it was save text. So I saved this as a CSV after I've already changed directories into that folder. I saved the name of it and then what it was, the data, and then delimiter is a comma for a CSV file. So now, let's see. I can just open this lookat array. Yeah. Yeah, you can save stuff quick. Open this lookat array.csv. And it's much cleaner to look at there. So another thing you can do is, if you want, you can change this in Excel. Like, okay, that number is wrong. I'm just going to delete that. Save it. Excel does not like CSVs, so it's like, are you sure? And now we can open it back up into NumPy with numpy.genFromText. You just give it the name, the lookat array.csv, and you also have to tell it again that it's going to be delimited by a comma. So it generated that from text. It opened that file and it downloaded it. And what we changed, we just deleted that, and so now it's not a number. It's your NA in a regular data set. It's called a numpy.nan. You can, in IPython, if you put a question mark in front of stuff, you can find out what it is. So this is, you do this for hours when learning. It's just looking at the documentation. So I can actually look at numpy.genFromText to see how it works by putting a question mark in front of it. And so up here, it tells me the options I could generate from text, all those different options. And so that could be, as well as your delimiter, you can add those options to it. And just the whole big data set. It's written by programmers, so it's never very fun to read. Sometimes you do have to open. This gives you examples of how it works. And if you're really anxious of how it works, you put 2 question marks. And it gives you even more, and it gives you the actual source code in NumPy of how, which you might need for advanced reasons. Okay, so our data could have that NaN in it, like this one. Just called it R. It's got this not available value in it. It's not a number. And if you do math on an array with a missing number in it, I tried to get the mean of this thing, and it brought back just NaN. So another thing to remember is just to do math on something with an NaN in it, they call it a masked array. Masked array. And then you have to tell it that this is not a number in the array. So if you turn your array into a masked array like this, you can do math if it has an NaN array. Does it what? Yeah, it just totally ignores it. Yeah.
Any end result based on that comes in anything.
Yeah. Yeah. It's like just clearing the whole cell in Excel. But it doesn't consider it. All right. Now you know a little bit about the fundamentals of NumPy. Do some science stuff. I expected more lab people to be here, but that's okay. You can still learn a lot. Let's go through these images. So this will be an image processing. Okay. So we import NumPy, and then, first I want to say what we're going to do. This image series here, say you're using a microscope, and you get all these pictures of your cells. And you stain for two different things. And there's a red stain and a green stain. And you took pictures of the cell at various time points. And your values of red and green, they're changing. It's two different proteins, and you're maybe wondering like if they're expressed differently over time compared to each other. So you can, since this is an RGB image, you can measure the red and green channels like that. So you don't always quantify immunocytochemistry like this, but if you wanted to, you could. So I just grab everything in the red and the green position, and I average it. Yeah, so a ratio, it does become a ratio. So I just importing these three libraries we're going to need. NumPy, Matplotlib for showing our pictures, and OS, which is Python's operating system module, which we're going to use for opening and saving files. And what's nice about OS is it's great to use because it's cross-platform, and I've made a huge program so far that you can completely share between Mac and PC as long as you use OS. That's basically all you need to share things with Mac and PC if there were besides really strange errors. So let's see. I'm actually going to get out of here and open terminal in our folder. All right. Import these things. And then something I'll call CWD is our current working directory. So that's where we are in this Brightwork class folder. And where the images directory are saved in current working directory, and then another folder called image time series. And so using the operating system module .path.join, I'm now making a new path of our directory plus that new folder. So yeah. All right. And then, since we have this folder with all the images, I want to list them so we can loop through one by one and do stuff on them. So I'm going to call all these items files. And so for each file in this images directory that we have, I'm going to list it. That's why it's in these brackets. So it's list file for file in this image directory if it ends with JPEG. And on a Mac, you have to do if it ends with JPEG even if there's nothing else but JPEGs in this folder, because there's a weird Mac-specific file that's hidden. So now I have these files, all our image files.
File for file?
Yeah, this is called list comprehension. So it would be the same thing as writing for f in os.lister, the images directory, add that file to a new list. So
Okay. So you're adding a few other files in the list.
yeah, I'm making a list. That's why it's in the brackets, and then inside I put the conditional thing. All right. Start by making some just empty lists that we're going to store our data in. I call it red per image and green per image. And then for each image that we listed in those files, what I'm going to do is use Matplotlib here, and its imread function is the same as MATLAB imread. And I'm going to read the file that's in the directory of images directory plus that image. So it's going to loop through and find each image. And then, so we talked about slicing. Basically, this image is now read into a NumPy array, and I'm going to get the red values out of it by looking at the image and indexing it all rows, all columns, which means all rows, all columns, all pixels. And inside each of those pixels, so the third dimension, just give me the R value. It's RGB, so 0, 1, 2 RGB, and so just give me that red value. I'm going to add the sum of the values, the numpy.sum of the values for each image into this red per image empty folder that we have. And then do the same for greens. Alright, and then I'm going to, since this was just a regular Python list, to use it, we're going to turn it into a NumPy array. And so you just call it the same thing as before, but make it into a NumPy array and give it a data type of float. We have integers and floating point values. So, just yep. All those red values, all those green values, now floating points. And I'll save a ratio of those, just dividing the two. So this red per image, it's going to be 16 items long because there's 16 images. And the ratio, you can divide these because they're the same size, 16 divided by 16, and it matches them up, which ones are divided by. And in Matplotlib, you start saying, I want to plot a figure, and I want this figure to have two subfigures in it. We're going to have our red and green and the other one, and so just like MATLAB, you subplot 2, 1, 1. That means you're going to have two subplots in there, and then this one's the first one. We're going to plot our data. It's plotted in the system right now. You plot, so PLT, this Matplotlib dot plot function, and the X values come first, and then the Y values, and then your options come after that. So your X values are this range from 0 to the length of red per images. The length of red per images are 16 images. So that's the same thing up here, just 1 through 16, 0 through 15. And so X values and the Y values are data, and we want to plot a red O. R means red, and then it's going to be an O shape. You can put a triangle or whatever you want, star.
That string, the RO string, is that what's going to be the title on the graph? Or is that
It's going to be, each point is going to be a red O as it plots along.
so that's like something specific to Matplotlib. Matplotlib interprets that and then
Yeah.
So if you said you make it, so you have like R X, then it might make it red.
Yeah, it would make red X's, red stars. Plot the next one in 2, 1, 2, and make it a black O. K is black. And then, so these are all plotted in the system. It's telling you that. And if you want to look at it, you just do call pyplot.show. It shows you your data. So overall, the images, you had more green, your green protein in there, but red is increasing, and so the ratio of red to green is increasing. So it seems like a lot of work to plot these things, but with Matplotlib. But once you have this, you have it for life. And keep plotting it over and over. I don't have MATLAB. Yeah. I just.
How much is that require?
It's $1,000 for one personal use.
How much is Python? All this Python stuff?
Yeah, it's all free.
Yeah.
It's all free. That's why I've been using it for so long. Started because somebody recommended it to me, and it's just I started actually doing web stuff. I was downloading stuff from a website online with Python, and so you can't do that as easily in MATLAB. MATLAB's a mathematical programming thing, and then the scientific community adopted Python, and so they have all these MATLAB-like and more modules available for free. And with Canopy, you have thousands of modules written all over the world that are just available to you for free. Things you can do rather than just worried about what MathWorks is developing.
I created that directory time series, but had actually moved in the images into it.
Oh.
I got nothing. Wow.
Did it not show up on the Dropbox? Just the whole thing?
Well, it just showed up there, but I
You're trying to make it? Yeah.
Yeah, I just created that directory in my home folder.
Yeah. All right. So, I promised doing some high throughput sequencing things that I've had to do for a lab before. So, say you're working on an experiment where you've got a bunch of random peptides, millions of random peptides, and you're binding them to a virus. And you would like to see, you've already bound them to a virus, and then you've sent that to the sequencing company, and they tell you that these are the ones that are bound to a virus, and at different strengths, obviously. But you have this list of all these that are bound to it. And next generation sequencing, you get a ton of data back, and so this is 1.6 million 7 amino acid peptides, or 1.9 million. And so NumPy will be great for doing math on all of these. Basically, we're just doing something simple. Let's actually go into this sequencing. All right. So we're going to grab all of this data, and it'll take a minute to read. Like before, we used delimiter comma. Now we're going to read this data, but there was an enter after each one, so our delimiter is going to be a new line in Python. That's /new, and you tell it that its data type is a string.
In real, I didn't use usually what I use
I'm using Sublime. I usually go Sublime, save this script, and then just run it from the terminal. Yeah. Yeah, it is in one place, but I just use Canopy to install stuff, and then I forget about it after. Sublime, I don't know. I don't use much of the features. It's a huge project. There's a ton of features, but my favorite one is multi-select. So if I select this, it tells me where all the other ones are. So if I change my mind, I don't want to call it NumPy anymore. It's just Apple D, Apple D, Apple D, Apple D, and I have all of them. And I can change them all at once. Call them NumPy 1. Yeah, I haven't used that. Is it Apple D in there? Or Control D? So, I print the size of it, told me there's 1.8 million sequences in there, and then we're going to calculate the molecular weight, and so for each amino acid of these proteins, these are all the molecular weights, and so it's a Python dictionary. A goes to this value, R goes to this, arginine goes to this value. And the function for calculating molecular weight is you're going to start with 0 molecular weight, and then so we'll call our protein, say it's a string like this. And we can list this protein, and it turns into a list that we could then operate on each thing for. So for each item in listing that, we're going to add to molecular weight the value of the molecular weight dictionary evaluated at that string, and then return it. Okay. Doesn't like my indent. So from there, we're going to, this function calculate molecular weight, we're going to make it into a NumPy vectorized function, which uses broadcasting, which I'm not totally sure how it works, but it means you're not doing things one by one. It's broadcasting over the whole array, and it can do things in the C language all at one time, and so it becomes faster. IPython doesn't like copy and paste sometimes, but if you use this magic function where you just write paste, it'll paste better. So now I vectorized that function, and now I'm going to run the function on all of our sequences. And it's done. Now we can get the molecular weight of all those and standard deviation of all those just using numpy.mean or numpy.standard deviation. So, vectorized function can be useful. It's not too much faster than going through each item because this is actually a one-dimensional array, but when you get into bigger dimensional arrays, vectorizing and broadcasting become a lot more useful. I'll show you that now, actually. All right. So we're going to look at one of those images we did earlier, and doing microscopy, and you'll see that sometimes you're going to get background. You know, your antibody had excess staining. You think that this low stuff is actually background. You don't want to see it because you're looking for a certain shape in there. You want to get rid of that background, and you looked at the pixels and noticed that the background stuff is green, but it's in the green value it has under 40. And so lots of this microscopy equipment comes with built-in software, Nikon and Canon and all that you can do stuff like this on, but it's really nice to be able to do it yourself. Just the great thing about being good at programming is like you just think of it and then you can think of a way to do it. So we are going to import some things. I'll just walk you through this script actually, and then I'll run it. I'm going to import the time module just because I want to time vectorize versus not vectorize and show you how it does become faster. And we've seen read the image, so there should be image 001 in this folder actually. I put it there just now, so you guys might need to do that to run it because I could read where it was before, but if I want to read it without using any of the rest of the path, I can just say read that image if it's in the same folder as your Python file. All right. So I'm going to record the time using time.time. Input time. Time1, I call time1 equal time.time. It's giving you the time in seconds since the dawn of man or something. It's a big number. It goes back thousands of years, I guess. But it's constantly increasing, as you know. So this would be an example of a vectorized way to do it. So we're looking at our image that we read, and we're going to index it. Well, I might as well talk about what a truth array is first. Let's look at truth arrays are cool. I use them quite often. So now we have this array, 1, 2, 3, 4, 5, 6. And then we can look at a greater than or equal to 3. A greater than or equal to 3. And it tells you, okay, in that array, false, false, true, 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 true. And so this is sort of the same as ones and zeros, false and true. And what you can do with that is index this array at places that is true. So we're indexing with a Boolean index array.
So you can index based on where that condition is trying to be true from. So I only want to look at things where the index. Look at things that have the index where this condition is.
Yeah, exactly. So we're going to index it again with that truth array. And so it's kind of like multiplying ones and zeros times this, because if that's a zero and it's false, it just goes away. So I do a lot of image processing, and I delete certain parts of it if my condition is false, or just remove it from the analysis, that sort of thing. So we're going to index with the truth array here, where we're looking at the image of the cell, all rows, all columns, R, G, B. So the green value is less than 40. And we're going to set those to 0. It's hard. It takes a minute to think about. So it's going to give you all of those values in an array, and then at the end we'll just call them 0, and so we're basically deleting them. All right. And then if you call time.time again, you're going to get the new time. So it's going to get it. It's going to do that function, get a new time, and then we can see the difference in time. This would be the way that you would do it with loops. For each row and then for each column, if that pixel is less than 40, turn it into 0. So it's not vectorized. And we'll time that. So I'll just.
I'm using some of the time functions, time, some of the stuff that I do. But just like time by time, just take the time by time snapshot and then time by time to just
Okay. So at the end of it, we're going to show the image after we deleted that stuff. But what happened was it took 0.02 seconds for the vectorized version. It took 2.47 seconds for the version with loops. And so that's 87 times faster with the vectorized version. So that's the difference. I've run scripts before that have taken, weekends or whatever. And so that's the difference between months and weekends.
Just being sure, the vectorized array is an operation every array is faster to do it.
Yeah.
Okay.
Yeah, it gets to use things that are beyond my understanding within C to make it work a lot faster. Okay, so it's not closing because this guy's still open, but now here's our image without the background stuff. If that was an organelle, we'll say, okay, there, that's its shape. Yeah, I have image J in here. What was I doing on image J? Forget what I was using it for. But there you can find pretty much anything on an image J within here, or you can build it. SciPy has an ND image library. Matplotlib has a lot of imaging things. Python imaging library is the biggest one. This comes installed with your Canopy. But yeah, it's got every function you need, and I'd rather type than drag a mouse around, basically. So people in my lab are using ImageJ right now to calculate the area around some cells, but that can easily be automated and do it quick. I would rather find a way to do it once in Python and write it, and then never do it again. Yeah. Just press play, you know.
That's not really right now. We're manually updating spreadsheets. This can be automated, and then I can run the script and have it take, have it take 1 minute and 0.75 seconds. Hours.
Yeah, I'm kind of addicted to automating things. I find myself, like, if I'm doing it like more than twice now, I'm like, try to automate it somewhat. And this is totally aside, but one thing that I saw recently is a new scripting language that will watch your mouse movements, and it uses image processing to see the buttons you're clicking on, so you can use an interface and click on a button, screenshot that button and code with that button. So you're telling it to click this, and then move this, and then open this different app, and then do this different thing. And so you can, without knowing any of the source code of all these different apps, you can automate like tons of things yourself. So try to learn how to use that. Sickly.
So in that last,
yeah.
That line 17. So that's what's actually vectorizing.
Yeah. I didn't have to make a separate vectorized function, just NumPy's stuff itself is built in vectorized. So.
A big time, because the loop method, that's what I've been using for stuff.
Yeah, that's how you learn to program, basically. Is doing loops and loops and loops. But yeah. Okay. So, this other thing, let's delete that, is I'm using this for some marketing purposes right now to make animated figures in Matplotlib, because you can look at data and then you can animate it over time, and it's just kind of something to watch. You can make it can be a video in your PowerPoint rather than just a graph. So open our standard modules and get this data from Excel. We're going to generate from text. It's got 8 rows and 300 something columns, and we're going to plot it, but instead of just plotting the endpoint, we're going to plot it over time so that we make a movie of it. So to neatly organize things, so you start making scripts and you want to put them into files so that you don't just have one file with a bunch of totally unrelated things into it. So I'm going to just make a new directory using Python's functions. So read this data. Time series tnsrs.shape. It's 8 by 375. And within the folder that I'm in right now, if this path doesn't exist, the current working directory that we're in and figs, use os.make the directory, make dirs, that, and then you can give it a name that's just, that fig dir is just going to be a string of your path. So, help organizing things. No. Doesn't. All right, and we're just going to get numbers because we're going to save each one of these files and we got to give it a name at the end. We might as well just increase the number at the end. So we're going to make a range, x range from 0 to the shape 1, which is 375. And then, so in this time series data, print I. So what happened here is for each item I printed, or for each item in there, I printed it, and it was considering one of these long lines of 375 numbers to be the item. What I want is for it to be the other way around. I want to use each column to be an item. This is going each row as an item right now. So yeah, and what will happen if I do plt.plot this? Show. The plot's way too much data. That's not what I wanted to see. What we want is the transpose of it, and so in Python it's just .t at the end of a NumPy array. So time series .t. Does that make sense? So now each data point over 375 columns, and then there's only 8 rows that it's plotting. So it's just plotting the other way around. You can multiply the whole array by -1 just to make it opposite so that things are increasing. I'm going to use that so that my data is increasing. All right, I'll show you a time point, an individual time point. It's going to be the 5th column. So that's just one of those columns. Alright. So for each row in this file that we're going through, and for each number in that range is just 0, 1, 2, down to 375. So we can loop through 2 things using this zip function. So now we're going for each item and then for each number in zipping together these 2 different arrays with the same size. So, okay, we're going to calculate the length of each time point, .shape 0, which should just be 8. And then we're going to make a new range from 0, or from 1 to 8, so from 1 to the length plus 1 of that we're going to use for x values, and then open a figure by doing the plt.figure. This is going to tell us that we're going to plot onto this figure. So let me just run this right now. It's going through each file now. I can just close it before it goes through all 375. What it plotted was our range 0 to 8 and our data and its color black, and it aligned it to the center. I gave the graph a title and I gave it an X label signal. This is a bar plot like this. It's a horizontal bar plot, that's why I called it plt.barh. Just bar would be up and down. But this is not going to work for our animation because it's like Excel does. It's adjusting your axis based on what the data is. And so your axis is changing all over the place. For the animation to look nice, we don't need all that to be happening. So we can just fix the axis. So we'll give it a limit from 0 to 100. It's plt.xlimit from 0 to 100. Close these. So these figures now. They're going to start and end all at 0 to 100, so it's not going to be jumping around on that axis like it did before. But, you know, we don't really need this stuff. Say this is for some marketing purpose and you just want to show data growing. You want to show a movie of your data. We don't really need these tick marks and all this other stuff that's distracting people. So we can turn off the axis in PyPlot. To do that, these are things that I looked up online basically. Is Stack Overflow. Just people have done it before. I googled how do you turn off the axis in Matplotlib. Yeah. So you use this. You call the axis this axis function, and then you use this set axis off function, and then to your figure you add axes with x. And so I mean, I would say Matplotlib is really not that easy to use. You should just have one thing that's like turn the axis off. So there's these three pretty weird things, but once you have it once, you just copy and paste from there. So we'll turn those axes off. Plot again. Well, while we're at it, let's add some text to here and kind of all of those. So now on this axis, I'm going to add text using Matplotlib's text function, and then it wants to know where to add it. And so I have 8 y values basically. So I'm going to plot this all at the 0 axis, and then at each y value. Just calling it, this is my bar number 1 and bar number 2, and color is going to be red because that's going to contrast nice against the black. You give a font size of 15 and make sure it's aligned right in the center of that bar. So, oh yeah, I want to go over, so save fig is what you do to save this. Before we were just doing plt.show, but if you just want to save it to a file, you do save fig, the directory, and your name. And then this %s here at the end is going to add that number, since we're in this loop that's also going through the numbers. If you do %s, so I couldn't just put a number here or else they would all be named the same thing. So this needs to be in the loop. So in the string you say %s, and then after the string you say %number. Make sense? Are you running it? Yeah. Yeah. Plotting them now. I'm printing each number. I wrote print number just to show me where I am within it. There are ways to suppress it, like sometimes you're doing something and it gives you a warning every time. Not an error, because an error will terminate your program, but it'll give you a warning, and so you import warnings and then set warnings off. So then you won't hear a bunch of noise. Yeah. So just open a few of these and you can watch them grow. I'll just wait testing. Yeah. G4 or whatever.
I quite that one. It's February 7th. So people don't take online.
Oh, yeah.
I spend a lot of time watching the beach balls and random stuff.
You don't have mountain lion, so you don't have swipe between.
I do, and I have swipe, but I don't. I mean, this touchpad couldn't handle that anyway. So.
Yeah. All right, so we'll open these and basically play a movie for you. What I did was just, when I did this before, is put it into a movie making software, and so each thing is a frame. And so you see your data growing. And so this is just a pretty figure that you can make with Matplotlib for marketing purposes or whatever. I'm at a biotech company right now, and so we sell a product. So my job is multifaceted. Yeah. So, anyways. All right. This is a pretty math-intensive thing. I'm not sure if you guys want me to go over but I can talk about it, introduce some of these functions. So, yeah, mine's huffing and puffing right now too for some reason. Basically, in pharmaceutical science, or a lot of different things, one of the things you calculate most often is an IC50. It's the concentration in which your drug has 50% effect. Inhibition, actually, IC50 is inhibition. EC50 would be the concentration in which your drug has 50% effect. And then, if you're using animals, you can calculate an LD50 where your drug has 50% lethality in the animals. So this involves using your data and fitting your data to a model, because you're not going to know it at exactly 50% until you draw a line through it and say, okay, that's where the 50% value is. So this is some data from a spectrophotometer viability assay for cells. And these are the concentrations of drug that we used from 10 and then down log concentrations to just PBS on the cells. And this is the data we returned about their viability from a viability assay. So I'm going to let's just do this together so you see. Here's one of these suppression things. NumPy set the print options. I'm suppressing some things, and I'm setting the precision for everything that prints to just 3 decimal places, so you don't see a bunch of stuff. Then these concentrations of drug and the data we gathered. So this, const nums basically is the same thing up here that I entered, except PBS. So each one of these was a number, and it split this user concentrations by that empty white space in there. If you add the list and then split at the end, it's just going to make a list out of it because of the empty white space. And then one of my favorite things about Python is this try, how easy it is to try something, and then if it doesn't work, do something else. So a lot of times you're coding and you're getting errors, like your script will run for a while, and then some error will come up and just terminate all the work you're doing. But if that next thing, you tried to do it, and then it failed, and then you just moved on, you would save the rest of your run. So I'm trying to evaluate this. So evaluate means I'm turning the string into a number. But it was going to say, oh, it's not a number when it gets to that PBS there. And so some error would come up, but then I just say, if that happens, except that number is just going to equal 0. So I made a new list out of that. All right. So another thing about dealing with files is we're going to open a new file. This is going to save a new file to the directory that we're in and call it ic50s.txt. It's going to be a blank text file, so you just say open this and write it. That's what the W is for, so we want to write to it. Alright, I won't go over this exactly. This is just one of the functions that's going to tell me where things are 50%. Yeah, I also looked up online in Python what would be a sigmoidal function. So I knew what a sigmoidal function was, but I wasn't sure how to type it in Python. But this is going to take care of that sigmoidal function for us. Yeah, I want to fit my model to a sigmoid. I think the data is going to start, and then there's going to be a big dip, and then it's going to slow down. It's S-shaped, basically. So this is a dose response what you do for drugs, and you use sigmoids a lot for that. So I'm also going to fit a polynomial to it, because sometimes sigmoid fails if your data is not exactly an S shape. It'll fail, and so you want to still use it, and you still want a model, so you can just fit a parabola to it. So I'm just going to fit like a little polynomial. It's sigma, yeah. Yeah, that's what we were doing too, actually. Yeah, what was Boltzmann? It's called Boltzmann, right? Yeah, the function. So I looked up that, and then I looked up Boltzmann function online. Sigma. That's that stats program, right? Yeah. Yeah, that's what we're doing. So this, if you just look that up and put it into Python, then you have a way to automate that, and you don't have to click stuff in your in your program.
So most of those scripts would be the idea of like if you got, say you give a certain dose and you get no response, but then once you reach the appropriate dose of nitrogen, you get a response.
Yeah. And you take your data and you make no response at 0 and the full response, the full amount of drug you gave it at 1. And so that's what this normalization is here. I'm going to take my data, subtract the last point, subtract the first point, divide by the last point minus the first point. It's just that's how you're normalizing it so that your data becomes 0 and 1 at the end. And NumPy.absolute is going to be the absolute value of those. Then I just save all this stuff, even if I'm not using it right now. I'll save that stuff for later, and so just NumPy.saveText. Join to this os.path.join that we used earlier. You can call it whatever you want, so you don't have to type that every time. And so from os.path, import join, and call it join to. You don't have to call join to, but there was already something called join. Yep, so I'm just saving that stuff again. Text file. This is just more math to deal with the sigmoid function. And
then we also use a scatterplot again. The sigmoid function to use to predict what the we use predict the concentration on that plot.
Yeah, an unknown drug or
we're looking for like a biomarker.
Okay, yeah. So if it acts in a similar way, you can use it to predict it. You'll get, you'll be able to, since you'll have the concentrations, you can predict what concentration, even if you didn't test it, might do this based on if it fits well. So that's why you make a model of your data using these things. SciPy.optimize.least square is going to be how you're going to make this model. Yeah. That's going to fit your model. And then you make your sigmoid function that we made earlier out of this value from your least squared, out of the parameters from your least squared. And so other things I've looked up is once you have your once you've done this least squares, how do you find the r squared from it to see if your model is going to fit? And so inside here, there's this info dictionary, which is, and if you grab this item from it and square it, that's going to be your r squared value. Yeah. And then that x for known y function that I wrote up here. This is going to be useful because I think if you were actually doing this thing in your lab, this is all hidden, I think, in Sigma how to do it. So it'll calculate it for you, but fine. Yeah, it saves it for you. Yeah, that's nice. So I'm going to call that x for known y, and it's going to find that at 50%. I'm going to write to this EC50's file just our data, basically. The EC50, the name of the EC50. So in this Python function, the name data. I'll show you later what that is. And then this number that's EC50. And I'm going to save it as a string. And this string, I don't want it to be a big with a bunch of decimal points. So %.3f, and then your number after the percent after your number is going to shorten it down. Yeah, it's 3 decimal points over.
A lot of that's right? That's like Python 2 point, Python 2 stuff. Python 3 is not that different.
Yeah, I haven't got scientific community, and I have not really gotten into Python 3 very much. It's the web community has. Not sure if I will. Yeah. Yeah, that is different. I think it's a little more easy to understand in 3 too. That's probably why they changed it. I'm going to make a new subplot, and then this axis that's going to be my subplot, I'm going to set its scale to log. And I'm going to make a scatter plot, the x values of the concentrations, and then those normalized values that we have. Size of these scatter plots will be 75, and then color. You don't have to enter K or R or whatever. You can do hex color if you want.
Size 75.
Yeah, I haven't really figured that out because this S equals 75 is much different than this MS equals 9. They're about the same size. So, yeah, you can probably do question mark scatter and find out what that is. The Y label, X label. Yeah. A grid is going to make this figure look nice. There's going to be a light grid on the background. I'm going to plot the same thing for a polynomial function. Because sigmoidal doesn't always work. And so that's this numpy.polyfit. X values, Y values. What kind of polynomial? 2 degree. So after I've defined these things, I'm going to run them. So the data is the data that we imported earlier. And the name of the figure is going to be this one. The name of what the CSV file is going to be that. And just to say it's a sigmoidal, that's for saving it. And this next one, you have to put the polynomial degree in there. So. Just run that. Saves the plots. This is our polynomial and our sigmoidal. Very similar. And I plotted the EC50 as that red triangle there. Saved that data to here, R squared. R squared's a little better for sigmoidal, and that's how you're supposed to do dose response anyway, so that's what you end up using. If you want to recreate this polynomial, you can make these figures in Python, but then you have to go back into the code to change something, and sometimes people will want to just use some other programs that they'll have more live plotting. They'll put the data in there and then they'll make this, and then they can tweak little things. So if I'm going to hand this data off to somebody and they want to tweak it, they would have to go into the code and tweak it, which they're probably not going to do. So yeah, that's why I save the data here, and then even the polynomial, I gave it the coefficients that you would need to plot it, so they can use it for publication or whatever.